With that, I think we can move on with our next presentation, which will give us an introduction about radiation hardness assurance. And our next presenter will be Viyas Gupta from the European Space Agency. So Viyas graduated with a PhD in radiation effects on space electronics from the University of Montpellier. He worked as a system engineer on CubeSats-related project as a young graduated trainee in the ESA education office, as well as during his PhD. He also worked as an education engineer at SatS on the development of new training sessions in different space fields for the training and learning program, as well as providing engineering support to the ESA Fly Your Satellite program. And currently, Viyas is working as a radiation effects engineer at SatS in the Netherlands and providing radiation hardness support to various ESA missions, from traditional ones up to CubeSats. And with that, we are looking forward to hear something about radiation hardness assurance at ESA. The stage is yours, Viyas.
Great, thank you. So first of all, again, thanks, Jan. Very happy to be here and share a little bit about what we do. Good morning, good afternoon, and good evening to all of you around the world. It's quite nice also to have such a worldwide audience. So hi to everyone. And so today I will be talking and introducing what is RHA, or Radiation Hardness Assurance, and how we approach this at ESA. And obviously, as you see in the beginning of the title, it will be a short one because 25 minutes is quite a challenge. But I hope that at the end of the presentation, you will be able to grasp a bit what we mean by that, how we tackle it. And I hope that I will be able to also introduce some points which are quite useful to keep in mind also for satellites which we call are built in the frame of the new space context. Okay, so let's start with first slide because, well, it's besides being nice and colorful, this is all the work that we do is for this, is to have great missions, nice science, and so on. But however, they are, as Luca mentioned in the presentation before, all in space, and space is not just a simple vacuum and quiet environment. It's harsh, and it's harsh in terms of radiation and ionizing radiation as well. And all these missions that I selected here, they all have in common that they were affected by radiation. And it's not only them, there are many, many more. Actually, all the missions, they suffer from radiation effects. Some of these effects can be benign or just transparent or transient, as Andrea was saying. Some can lead to resets or power cycle or reboots or switch to redundant units and so on. And some really can lead to a whole mission failure. And that's actually the final goal of RHA, is to, from the point of view of radiation, to try to spot the risk, to assess it, and then to mitigate it to the level which is defined by the project. Is to limit this risk as low as possible, as defined by the project. Okay, so the first question and the most important one for this lecture is, what is RHA? And then for that, when we don't know a word, we go to a dictionary. And here, for space in Europe, one of the go-to tools is the ECSS standards, are the ECSS standards. And in there, that's the definition that we have of RHA, so Radiation Hardness Assurance, is that it consists of all activities undertaken to ensure that the electronics and materials of a space system perform to their design specifications after exposure to the space environment. And I highlighted all the important words here. One of them is also that I will be talking about a lot EEE parts and electronics, but radiation also affects materials and should also be kept in mind. Obviously, also biological cells and astronauts, as we've seen before. And then here we see that it's all the activities. So all the aspects that we will be covering in the workshop are part of the RHA, let's say, framework. So radiation hardness assurance, it's a PA discipline, yes, but it also very closely linked to the way your system is designed. And so the RHA engineer reports to the PA manager in the project, but also discusses with many other experts, system engineer, part experts, and so on, electrical engineers. So what do we deal with more concretely is many different topics. It goes from radiation environment definition, as we saw in the first presentation, to try for when we have a satellite to define what's the radiation environment in this given orbit. And for each different orbit, each different mission, you have a different radiation environment. Then it deals with also the requirements, because that's really what we design for, are the requirements, and it's very important to properly design them, to define them. So there are mission, system, subsystem requirements, but also radiation requirements. Then it deals with also the layout, how the part is within the whole satellite. It deals with also how to improve the design, how to mitigate the errors once they are spotted, or effects once they are spotted. It also deals with part selection and try to go towards parts that are robust to radiation. And also one important aspect is about testing and how to properly test. And in fact, all these, most of these points, you will see them, or you've already seen some of these lectures during this workshop. Okay, so after that, basically, I've covered my objective of letting you know about what is RHA. But of course, there is a lot more to say, and I will try to highlight some of the most, I think, are useful things for you to keep in mind. And the first one is that here we are all talking about risk. It's all about risk and focusing here on radiation. And that's very important to keep in mind, because we can define radiation hardness assurance level differently from a high-class, very top-notch space mission to a more educational mission. So the RHA requirements can be tuned depending on the criticality of the mission, and the criticality is linked to the risk. So this all depends on your requirements, the mission, the environment, the requirements which are related to reliability and availability, also the criticality of the equipment within your satellite. If it's highly critical, it may require a high attention in terms of RHA, for example. Okay, and for that, in order to assess this risk, it's very important also to have a good knowledge of what is the risk beforehand for your mission, for your equipment, and to consider this risk within the constraints that you have from the project with regards to budget and criticality and so on. And all this allows to define what will be your RHA plan. So what we have at ESA is that we have what we call, when we work on a mission, an RHA plan that is issued by the industry we work with, where they define how they will do. And it's a response to what we call a PARD, so a PA requirement document. But this plus the requirements basically somehow allows us to have an understanding of what is the risk we are wanting to, how much we are wanting to limit the risk from one project. We can be different from another one. And an important aspect to be able to assess this risk is radiation test data. A lot of the time, and very often, we need radiation data to be able to assess the risk. So what I usually say is that no data, no RHA. Means that if we don't have radiation test data, it's very difficult to estimate how can be the risk for that part in that environment for that mission. So the question is, where does this risk lies, with the project or with the radiation engineer? And that's a very essential point to be addressed at the beginning of a project, so to be able to have enough resources to be able to further act on all the different activities, for example, and including radiation testing. So when do we start RHA and how do we do? Because sometimes we hear, radiation is linked to environment. We do it in the phase when we do environmental testing. And that's actually not correct at all, because RHA and the whole RHA aspects, they start from the very beginning of the project. And most of the work that we do ends up at CDR. CDR is when you have defined and finalized your design, and then you're ready to start manufacturing and then testing and so on. So really, it's at this stage, at the end of phase C, at CDR, where most of the work is finished, and it starts really at the beginning. Some little work goes afterwards, but it's a detail at this stage. So it's all about interacting with the PA, the engineers, the industry, and so on, and iterating on all of this. So it's an iterative process, and the earlier it starts, the less problems you have. And I will quickly introduce in my presentation that this radiation analysis report, which is the most important document that we have for radiation engineers, where we look at an equipment and we see all the equipment for a mission. So we look from the point of view of radiation at how it responds to radiation for that specific mission. Of course, there are many other documents and so on, but I will not go into the detail here. And then I will also introduce an important review for us, which we call RCB, a Radiation Control Board. And it's, in simple terms, a sort of a CDR that we do for radiation. So some of you, I hope, are familiar with all the usual project phases in the space world. So we have phase A, phase B up to PDR, phase C to CDR, phase D and E. And then here we go a bit more into the details about, in this V cycle, just wanted to highlight to you where most of the RHA activities they lie. And they lie really just before where we start to have a detailed design, and stop almost all activities stop before the implementation. And you see that even though the work starts very much at the beginning and can include preliminary studies, when we go through, the most of the activities are during this phase C up to CDR, where there we need to have all the radiation test results to be able to do all the analysis, to be able to assess the risk, and to be able to summarize it to the managers overall. And then there's some minor activities then later, but again, out of the scope of that mission. Here is a timeline, a temporal timeline, to give you a better idea also, where we start here, preliminary activities if needed. At preliminary design review, the work starts to be to converge up to CDR, and that's where, close to CDR, we have what we call an RCB, a Radiation Control Board, that I will explain a bit more in detail. But that's where most of the activities are, and then some additional ones a bit later. And it's only later, very later afterwards, that we do environmental testing. So in requirements, it's difficult to talk about requirements so briefly, but they mainly come from three domains: the environment, the risk, and the mission objectives. And all these then can be, propagated through different topics: destructive effects and permanent effects, margins, error propagation, availability, reliability, and RHA methodology. And all these are part of the requirements that we use and to which we have to verify the work at the end. And so to do that, we have what we call the radiation analysis report, as I mentioned before. And so I said it's a document where we list all the radiation effect, impacts, test data, all the information we have in terms of radiation for a given equipment to be able to assess the risk. So what do we put in the radiation analysis report is we put the applicable documents, obviously, but also all the parts that we believe are sensitive and to which effect. And as Andrea mentioned briefly also, like some parts can be affected by different types of effects. So we need to be as exhaustive as possible there. And then we record based on the modeling of the environment and so on, what are the levels received for each part, what's the environment, how did we model it, what is the margin that we are using, and is the margin for total ionizing dose and total non-ionizing dose, is this margin met? And then we analyze the effects of drifts, of parameters. Can the design cope with them? Do we need to add mitigations? And for single event effects, we discuss the assumptions, the test data, how the calculations were done, how these effects propagate, and how this mitigation can avoid the propagation when it is very critical. And we obviously assess these effects for destructive and non-destructive effects, of course. And at the end, we also overall, based on all these assessments, assumptions, data, we usually combine it to have an idea of the availability of the equipment, because it's usually an important requirement. And we need to add the radiation-induced availability contribution that we look at in this radiation analysis report. And at the end, we obviously conclude with regards to the project requirements. So we do this through this document, and I mentioned that we review this in this sort of radiation CDR that we call a radiation control board. And how does this happen? So first we need input documents, and we have a matured declare component list, a design which is matured, and like cheese, the more mature it is, the better. Then we have the radiation analysis, which now you know a little bit what it is, but also test reports and other documents to assess the impact of some effects, the worst case analysis, the path trace analysis, the environment, the shielding, etc., etc. And with all these inputs, we assess part by part all the effects, all the assumptions. Do we agree or not? Do we agree on how the levels were calculated? One important activity is going through the test reports to be able to assess whether they're applicable or not. And we will go through that, but we check traceability, the test conditions, is it worst case or not? And some of the things are not obvious when you don't know. And then we do the assessment at equipment and system level, because that's the most important. What we are interested in eventually is to be able to assess how it will impact the equipment and overall the whole satellite and the mission, and so on. And after this, if the assessment is positive, we say, okay, green light for this equipment, using those parts for this project in this environment. Of course, if anything changes, we need to do a reassessment. So why do we look at propagation? As an example here, let's say we have a subsystem here with many different components, all of which can be affected by different types of single event effects. And let's assume here that we are using this great SRAM new technology where we have still an ECC to correct errors, but here we have a double bit error. As Andrea mentioned, like some particles can create several bits of errors. And this error can propagate to the microcontroller, to the periphery interface, propagate to the CAN bus, and can go outside this equipment. And maybe if this bit was storing or not the activation of your propulsion unit, this could have potentially very negative consequences, for example. So that's why we need to always assess the effects with respect to the design. They are highly dependent on the way your design is built. And so we do this assessment for TID, total ionizing dose, and total non-ionizing dose, which we call also displacement damage. I don't go through all this, but basically it's a loop where we assess for the device the data and how the parameters, if they degrade through worst case analysis, whether or not the system can cope with them. And then we can see whether this is acceptable or not. Do we need to mitigate? One way to mitigate can be to shield or to change the parts or to update the design to be able to withstand these degradations, and so on and so on. So it's an iterative process. And for TID, I wanted to introduce some two important concepts, which is part-to-part variability and lot-to-lot. And here we can see an interesting figure from a study of a colleague where for the same parts from that lot, several samples were tested, and you see how different they can be. And it's really not predictable. And in gray, you have the response of each part. In red, you have what we add as a statistical analysis to be able to ensure that the part that will fly will be within those limits. And you see that we cannot test many samples, but if we test too little, there is a risk that we don't sample the, let's say, exotic ones which have exotic behavior. And then what if we fly this part and have tested only this? Then we are out of spec much earlier, and then we have an issue. That's why we need to test a lot of parts. And the same thing goes for the lot to lot. If we have the results from one lot, it doesn't mean that we can predict the result from the other lot. As you can see here, the response can be very different. And of course, for TID, biasing conditions, those rates are all very important effects to be considered. Similarly, for single event effects, we assess not only based on the data that we have, but also how these effects affect in terms of criticality the component or the equipment, and this allows us to decide whether or not this part is fit for that project. And in terms of SE, a quick word on destructive effects is, in space, we are very conservative. We try as much as possible to avoid destructive or potentially destructive effects. Here you can see a picture where, due to a single event latch-up, you had a vaporized wire bond because of the high current, which led to the melting of those. And why we avoid destructive effects? Because it adds more difficulties in terms of adding redundant component or system, not being able to check all different types of issues, in particular latent damage. And some destructive effects can simply not be mitigated. But in some cases, as Andrea was mentioning, we can mitigate with derating, with limiting the current, with autonomous resets or power cycles, and so on and so on. We can, but to be sure, we need to have the test data to ensure that these mitigation are able to mitigate those. And of course, one important aspect is, even if effects are non-destructive, we always need to consider the risk of latent damage. So in very low risk mission, this becomes a very important issue. And then that's where we really say no to destructive effects almost all the time. When we have non-destructive effects, what do we do is, on one hand, we take the environment and the models. We take the test results of the components and the cross-section introduced before, and we combine this with some models and methods to be able to have an error rate. But be careful about this error rate because it's an average value. So it's a value that you would get on a long time scale, but it's not a value for a given instant. And for example, here you can see these are actual data from the ProbaV latch-up experiment from a colleague, where you can see that the errors, they vary. Even if you have the theoretical number of 6 events per day, here you have the different latch-ups that can vary, sometimes higher, sometimes lower. And this is the type of response that you can get in low Earth orbit, where you have lots of errors in the South Atlantic anomaly and some on the poles. The most important takeaway here is that, for example, even if you have a memory which predicted only one event in 40 years, okay, well, this can happen within the first month of your mission, or this can happen within the first year of your mission, because the probability of an error is the same from the beginning to the end of your mission, and that's different. So be careful about that, because these are stochastic events, as Andrea mentioned before. Some important aspects that we use here is conservatism in terms of margin and modeling. We are very careful with heritage, because heritage cannot be applied in all cases. And understanding and defining proper requirements are very important to be able to do the work. The part response and understanding how a part responds to radiation is very important. Some parts are inherently insensitive to some effects and some parts are not. It's important to know this. And be careful also about radiation hardened, radiation tolerant, and COTS components. Automotive COTS components are not necessarily more robust. Radar components doesn't mean that you need to neglect radiation at all. And traceability, as we discussed earlier, is also an important aspect to be considered. For example, here, 2 COTS components were, due to lack of traceability, one was tested on ground with high insensitivity, and one was flown in orbit with low sensitivity due to change of dye, which was transparent to us when we purchase. And that's one of the major risks of COTS components. And that's why I try to highlight this under this image, is to say to be careful and not to underestimate the hidden cost of COTS, especially if you need to use these COTS components for critical applications, because it's cheap at the beginning, but later on, if you need to test it and characterize it, it may cost you a lot. And here, a radar part, we see it's radar, great. Shall we close our eyes? No, because it can be also sensitive to transients, which can potentially propagate. So we always need to be on the lookout and also for these details. So once we have the environment, we go for testing, but I will not go into the details because that's the next lecture, future lecture. We do photon cobalt testing and high energy proton and heavy ion testing. But one important message I have here is we use the TINA approach. Those of you who know this reference from Margaret Thatcher may understand this. For us in space, we say that there is no alternative in the testing methods currently for space application. We need heavy ion and high energy proton for SEE, cobalt for TID, and high energy proton for TNID. And of course, we are open to new methods and so on. But at ESA, for space applications, we remain conservative because we know that these work. There are some, of course, limitations even when we test, and that's why we stick to those type of testing. And with that, I will conclude. New space, because most of you, I think, are in this new space domain, doesn't mean that you should neglect radiation hardness assurance or good practices. It should be considered now. I hope you understand that from the beginning of the project and not keep it under the rug until the end. And then it has its own challenges which needs to be properly understood from the beginning. So be careful about that. And what you can do is talk to people who have the knowledge, companies, engineers, and be aware of these challenges as early as possible, This will help you to build a good and reliable system to be used on challenging missions. Here are some standards that we use in Europe. And I would like with that to thank all the support from my colleagues for some of these slides. And with that, I thank you all for your attention. Thank you very much.
We need to thank you very much for your nice presentation, Viyas. I think we really got a nice introduction about radiation hardness assurance seen from ESA point of view, and how important radiation hardness assurance comes or become, specifically if we're talking about new space and when people are really focusing or are in the need of using commercial off-the-shelf or COTS electronics. We are good in schedule, and I think there's room for maybe one or two questions.
Sure.
I received one question from the audience, which is regarding TID. So do you think, or it is an anonymous question, so the question is TID still of concern for LEO, even in case that COTS components are used?
Yeah, so thanks for the question. So TID and TNID are effects which are cumulative. So contrary to single event effects, which are stochastic, random, they will progressively degrade your component. So if it's important in your mission to know how much your component can withstand, to be sure how long your component can withstand that environment, is yes. But most of the time, some of the missions are have small durations and then will accumulate less TID. In that case, for some projects, you can take more risk and you can accept not to do TID testing and to simply cross your fingers that you will not have components which are extremely sensitive. They are maybe not all, but you can be unlucky and have them. But if you have to choose between TID and SEE, go for SEE, because SEE can happen from the first second your satellite is in orbit. I hope I answered the question.
For me, very clear. And maybe one last question. What energy range is considered as high energy for proton in testing for space applications?
So also interesting question. For high, when we say high energy for protons, we aim at 200 MeV, so mega electron volt or so. Why is that? If you recall Andrea's presentation, is the higher the proton energy, the more chances you have to be able to generate secondaries that will have them a higher LET to generate errors. So if you test with low energies, you may not be able to trigger all the errors, and you may have a wrong confidence on the robustness of your part. And on that matter, actually, one thing I didn't mention due to time is that when you do proton, even high energy proton, you may not be able to see all the possible destructive effects a part can have in orbit. And that's why usually the go-to when you want to really assess the risk is to perform heavy ion testing, which is the best way to be able to assess, in particular, all the types of effects, but in particular, destructive effects.
All right. Thank you very much again for your presentation. Again, to the audience, we received multiple questions, and as I said in the beginning, those questions are not lost. So we are collecting all the questions, and those of these questions that we haven't distributed yet to the presenters will be distributed afterwards, and hopefully we can come back to you again.